welcome. In today's lecture, we're going to cover Chapter 20, Carboxylic acids and their derivatives. In the last chapter, we studied ketones and aldehydes, and so in this lecture, we're going to finish the rest of the carbonyl compounds and go through all of the derivatives of carboxylic acids. Carboxylic acids are abundant in nature and found in a wide variety of synthetic pharmaceuticals. Here are some examples of carboxylic acids that you might be familiar with and are widely used. For example, acetic acid, or white vinegar, and acetyl salicylic acid, or aspirin. Acetic acid is widely produced, and it's a precursor for vinyl acetate, which is used in paints and adhesives. Industrially, it's produced by taking methanol and carbon monoxide and with a rhodium catalyst forming a carbon-carbon bond as well as the full structure of acetic acid. So as always, we'll begin by going through the naming procedures for these compounds. Butanoic acid, we can start with our root. We have a 4-carbon root, so we have butane. And then our suffix for carboxylic acids will be oic acid. So it's a bit longer of a suffix than normal. And we can see here with this molecule, once again, we have oic acid. We have our longest linear chain of 5, so it's a pentane. And we're going to position carbon number 1 so that the carboxylic acid has the highest priority and is at the lowest position. So comparing the carboxylic acid to the hydroxyl, the carboxylic acid will have higher priority. When we have our carboxylic acid attached to a ring, then it's going to be named as an alkane carboxylic acid. So this would be cyclohexane carboxylic acid. And we also have several carboxylic acids which have common names. These are the low carbon count carboxylic acids like formic acid, acetic acid, propanoic acid, and butyric acid. And then also when we have a benzene ring directly attached to a carboxylic acid, we have benzoic acid. In some cases, we might have a diacid, and when we have 2 carboxylic acids attached to the same molecule, then our suffix will be dioic acid. And we also have a slew of common names for the most simple diacids. So we have oxalic acid, 2 carbons, malonic acid, a 3-carbon diacid, succinic acid, 4 carbon, and then finally glutaric acid, which is the 5-carbon carboxylic acid. Our carbon on a carbonyl group is sp2 hybridized, which leads it to having a trigonal planar geometry. On a carboxylic acid, we have both Lewis basic character and Lewis acidic character, which also leads to Bronsted basic and Bronsted acidic character. That means that 2 molecules of carboxylic acid can hydrogen bond with each other, and this will increase the boiling point of carboxylic acids relative to alcohols because of this hydrogen bonding that can occur. Carboxylic acids are weak acids, and so in the presence of a strong base we can deprotonate them, and then they will exist as their carboxylate salt. The salts can be named as well. So for example, the sodium salt of benzoic acid is sodium benzoate. So we use the -ate suffix when we're referring to the salt of a carboxylic acid. In water, we'll have a slight dissociation, so there'll be an equilibrium here, and notice the equilibrium is in favor of the protonated carboxylic acid, but there will be a slight deprotonation. And we're going to have a pKa range of carboxylic acids, generally between 4 and 5. This is really between like 3 and 5, and it really depends on the functional group that's attached to the carboxylic acid. So for example, if we have a benzene ring attached, it's slightly more acidic than just acetic acid. And we can further modulate that acidity, and we'll go through that in a minute. But in general, carboxylic acids are weak acids. So compared to a strong acid like HCl or sulfuric acid, we consider them weak. Compared to an alcohol, which has a pKa somewhere around 12 to 16, they're going to be relatively acidic. The equilibrium between a carboxylic acid and its carboxylate anion at physiological pH will be roughly 1000 to 1, and this can be calculated with the Henderson-Hasselbalch equation. But the combination of an acid and its conjugate base act as a buffer system. For example, pyruvic acid can exist primarily as the pyruvate anion at physiological pH, and because of the overlap between different carboxylic acids and their acid-base pairs at the ability to buffer at physiological pH, many of them play an important role in biology. And in your biochemistry class, you'll further explore the biological role of many different carboxylic acids. I hinted before, depending on the substituents attached to the carboxylic acid, the pKa will differ. And this is due to the inductive effect. So here we have chlorines being added. The more chlorines we add to acetic acid, the more acidic acetic acid will get. And this effect falls off with distance. So the further the chlorine is away, the less acidic it is relative to chlorinated acetic acid. We can also modify the substituents on a benzene ring. If we have electron withdrawing groups, such as a nitro group or an aldehyde, that's going to make the carboxylic acid more acidic. And if you use electron donating groups, it will make it slightly less acidic. Next, we're going to look at some reactions. These reactions are methods to prepare carboxylic acids, and these first are all a review. So from chapter 9, we can do oxidative cleavage of an alkyne, cleave this triple bond to form 3 carbon-oxygen bonds on each side of the triple bond through oxidative cleavage, and the oxidative cleavage will yield us 2 molecules of carboxylic acid. If we take a primary molecule and use a strong oxidizing reagent, we can oxidize from the alcohol all the way up to the carboxylic acid. And the carbon in the benzylic position next to a benzene ring is going to be susceptible to oxidation. So in this case, we cleave both of these carbon-carbon bonds and take the carbon all the way up to the carboxylic acid. Remember, the requirement for this reaction to occur is at least 1 proton in the benzylic position. Last chapter, we looked at an additional reaction that can form carboxylic acids, which is the hydrolysis of nitriles. If we take a nitrile and expose it to acid and heat, it will hydrolyze to the carboxylic acid. And so this allows us for a two-step synthesis of carboxylic acids where we can employ a cyanide anion to do an SN2 reaction with a good leaving group, and then follow it up with hydrolysis to yield our carboxylic acid. This reaction, the carboxylation of a Grignard reagent with carbon dioxide, we actually did in lab last semester. If we take a Grignard reagent and react it with carbon dioxide, then we'll have nucleophilic attack at the carbon, followed by protonation will yield us with, and an acidic workup will yield us with the carboxylic acid. So this allows us another method to convert an alkyl halide to a carboxylic acid. First, make the Grignard reagent, and this is the exact example that we did in lab. And then second, add the electrophile, which is carbon dioxide, to yield the carboxylic acid. We have a few reactions that we can review of carboxylic acids as reagents. So we have lithium aluminum hydride, which we discussed several times is a reducing agent that can reduce a carboxylic acid all the way down to the primary alcohol. It's a strong base, so first it will deprotonate the carboxylic acid and form the carboxylate anion, and then we'll have a reduction of the carboxylic acid down to the aldehyde. Once that occurs, we can have a second molecule of hydride undergo nucleophilic attack at the carbonyl carbon and form a tetrahedral intermediate, which when protonated gives us the primary alcohol. We can also use BH3 instead of LAH as a chemoselective reduction. So in this case, we can look here at the molecule. We have a ketone on one side and a carboxylic acid on one side. If we expose it to BH3 and THF, we will reduce only the carboxylic acid and not the ketone. So in all of these reactions that we've looked at, the reductions, we have a change in oxidation state of the carboxylic acid down to the alcohol. But there are some reactions where we will, instead of a reduction occurring, we'll have more of a substitution occurring. We keep the same oxidation state, and we replace the oxygen of the OH with the heteroatom. So these are going to be what we consider as carboxylic acid derivatives. And we briefly reviewed these carboxylic acid derivatives in class this week, but we're going to go into further detail now. Here are the four main carboxylic acid derivatives: the acid halide, acid anhydride, ester, and amide. Any carbon with 3 bonds to an electronegative atom is considered a carboxylic acid derivative. So at first glance, a nitrile might not seem like a carboxylic acid derivative, but it would fit the criteria. Acid halides and anhydrides are very reactive and relatively unstable, and we'll go through the reasoning behind their reactivity. So they're not as common in nature. But esters and amides are very common in nature. Esters are also responsible for many smells. Proteins are comprised of repeating amide linkages, and so this builds many of the biological structures through these amide linkages and the folding of proteins. This hormone melatonin also contains an amide, and there's many natural products that contain both the amide and ester linkages, as well as carboxylic acids throughout them. So let's take a moment and go through the naming procedures for acid halides, esters, and amides. If we look at an acetic acid, if we want to name the bromide version of it, we'll change the ic acid to il halide. So our new suffix. So instead of acetic acid, we'd have acetyl bromide. Instead of benzoic acid, we'd have benzoyl chloride. And similar to a carboxylic acid on a ring, if we have the carbonyl chloride on a ring, then our suffix becomes cyclohexane carbonyl chloride. Anhydrides will just replace the acid with anhydride. So the ic stays the same, but we just replace acid with anhydride. So we have succinic acid, succinic anhydride, acetic acid, acetic anhydride. There are also mixed anhydrides. So if we have a mixed anhydride where two sides of the anhydride are different, then for our naming convention, we will have both the roots of the each side of the anhydride. So this one would be an acetic benzoic anhydride. Esters are named based on the alkyl group attached to the oxygen followed by the carboxylic acid's name. And we're going to switch the suffix to ate. So instead of acetic acid, we have an ethyl group attached to the oxygen, so it'll be ethyl acetate. And for our diacids that are converted to esters, we would have diethyl, one for each side, and then malonate. We're going to have the same trend when a cyclohexane derivative or ring is connected to the ester, where we start with the what's attached to the oxygen. So this will be a methyl ester, a methyl cyclohexane carboxylate. For an amide, we're going to replace the ic or oic acid with amide. So instead of acetic acid, we'll have acetamide, or instead of benzoic acid, we'll have benzamide. And if we have the amide attached to a ring, then we'll start with the name of the ring, followed by carboxamide. In some cases, on the amide, we will have substituents on the nitrogen. And if this is the case, then we will begin with the substituents as on the nitrogen. So this would be an N-methyl, because we have a methyl group on the nitrogen. And in this molecule, this would be an NN dimethyl, because we have two methyls on the nitrogen of the amide. And finally, nitriles are named by replacing the ic acid with O-nitrile. So acetic acid, the nitrile version would be acetonitrile. And for benzoic acid, the nitrile version would be benzonitrile.